Okay. Um, well, last time I started to tell you the first strong evidence that matter was made of atoms. And you remember the first really direct strong evidence came from this law that Dalton discovered, that the law of multiple proportions. And basically what he found was this integer relationship in terms of the mass of different elements that combine to form compounds. That whenever you had several compounds that could be formed from the same elements, if you looked at the ratios of the masses that combined, they were in simple integer ratios. And we saw that with, one of the sets of compounds that we saw that with was the compounds of nitrogen and oxygen, right? That I told you about this chemist Humphrey Davy that discovered nitrous oxide, which is laughing gas. And then there were several other compounds that we looked at that were all nitrogen and oxygen. But for a given amount of nitrogen, the amount of oxygen varied in each of those compounds. And it varied in these simple integer ratios. If you had 1 gram of oxygen in nitrous oxide, say, you would have 2 grams in a different gas called nitric oxide. And then you would have 4 grams in yet another gas that you could make, and 5 grams in this white powder that you could make. So I told you all that last time, and it makes a very convincing, it makes for strong evidence in favor of the atomic theory, because if you think in terms of atoms, there are just these nitrogen atoms and oxygen atoms, and all nitrogen atoms weigh the same, and all oxygen atoms weigh the same, then this law that Dalton discovered would have to be true, because you can only have integer number of atoms, and that's going to mean that compounds have to be these integer weights, weight ratios that Dalton discovered. Okay, now, last time I went through all that pretty quickly, and I told you a little bit about how these different nitrogen-oxygen compounds are actually made, but I didn't tell you that much, and I thought just to give you some insight into how complicated chemistry is and why it didn't really develop until the early 19th century or the late 18th century. I thought I'd tell you a little bit about how you can actually make laughing gas. All right, now, one way to make laughing gas, the most direct way to make it, wasn't discovered until the 20th century, early 20th century. If you just take nitrogen and oxygen, and you in gas form, and you put them together under really high pressure in the presence of some catalyst, and it turns out that iron oxide works pretty well, that you can get them to combine into nitrous oxide. Now, the reason that wasn't discovered until later is because you actually need pretty high pressure in order for that to work. A lot higher pressure than standard. And so that wasn't the way that laughing gas was originally made. So I'm going to tell you a little bit about the way it was originally made. In nature, you can find certain salts that are called ammonium salts. And they have a compound in them. There's a part of that salt that is ammonia. Now, you've all smelled ammonia gas before, right? It's in a lot of household cleaners. You get that that ammonia smell. Okay, well that naturally occurs in certain salts, and there's you can find, for instance, a white powder out in nature, ammonium chloride. Okay, so let's start with ammonium chloride. Now, so chemists found that there was this stuff, ammonium chloride salt, sort of a whitish powdery material. And if you took that and added water plus this other whitish, chalky material called lye. Let me see. You could get this combination to go into sort of salty water plus let's see, ammonia gas. Okay, so this ammonia gas would bubble up. And if you took this ammonia gas now and you added, so I call this, you can call that step 1, okay, and you get the important product that you get out of that is the ammonia gas. Okay, now in step 2, if you take the ammonia gas and say you add to it nitric acid. I think I told you that there were 2 acids that were discovered way back in the Middle Ages, sulfuric acid and nitric acid. Okay, so people knew how to, they knew how to get nitric acid at this point. Well, if you dissolve the ammonia gas in the nitric acid, you get what came to be called ammonium nitrate. Now, so this is a, let me see, what, this is actually distills out as some kind of powder, okay, so it's actually a solid. Now, if you heat it up, turns out, you can, okay, so let's call this step 3 now. Take your ammonium nitrate plus heat, if you heat it to 166 degrees Celsius, you get nitrous oxide, laughing gas, plus steam. So now you have to just cool it down. Steam condenses into water, and you're left with the laughing gas. So that's the original way that that chemists discovered this compound of nitrogen and oxygen. Yes.
Humphrey Davy did to get
Yeah, he did something at least a lot like this. Right around, I think it was 1799 or something, or 1798. He was actually working in a medical facility, and they were looking for gases that would make their patients feel better. And this one seemed to work, at least short term, to make the patients feel better, but I'm not sure it actually cured anybody. But it was used to relieve pain for a while. Okay, but you get the idea. See, chemistry is this, see, at this point, when Humphrey Davy first managed to make nitrous oxide, there's no real theory in chemistry at this point. And you can see how complicated the subject is, going from one substance to another, to another, to another. And they didn't really have a way of being able to predict and understand these transformations. So at this point, the subject is really, it's very complicated. It's, the chemist has to just remember, all these transformations that he's seen or that he's heard about. He hasn't got really a theory to guide him. It's really chaos. And it wasn't until people started being able to, after Dalton, when people started thinking in terms of the atomic theory, that they could start making sense of all these reactions. Okay. Now I started to tell you another major piece of evidence for the atomic theory last time, and let me continue that. First, since I just told you about the laughing gas, I'll tell you one more thing about it. If you take laughing gas and you heat it up really hot, I forget what temperature you have to go to, but at a certain temperature, it breaks down into something a lot like air. It just turns into regular air. Regular air that's oxygen rich. Say it has what happens is if you take 2 liters, say, of nitrous oxide and you heat it up a lot, it goes to 2 liters of nitrogen plus 1 liter of oxygen. Now, what is ordinary air? Do you know? I think I mentioned once or twice what it's just a mixture of oxygen and nitrogen, right? But I mean, for the most part, it has other small elements of other things in it. But what's the ratio? You remember, Daniel?
N2O?
Well, that's what this is. But the mixture of nitrogen to oxygen, air is actually mostly nitrogen. Right? I told you that. So do you remember what the mixture is, Evan? Yeah, basically, well, it's not, don't think of it as that. I mean, I've written symbols like that, but that's the symbol for a compound. Okay, this is just nitrogen and oxygen. They're not hooked together. But yeah, it's a ratio of about 4 times as much nitrogen as oxygen in ordinary air. So breathing this stuff would be, you would just be getting more oxygen than usual. But, you could breathe it fine. Okay. Now, the other thing that I've told you before is, say, in the original Cavendish experiment, Cavendish found that he could make water, right, if he had 2 liters of hydrogen and 1 liter of oxygen, how many liters of steam does he get?
2.
2.
How do you know if you get 2 liters of steam?
Oh, well, if you keep it at the same pressure, okay, then that's how much volume the steam will take up. So yeah, when I'm talking about volumes of gases here, I'm assuming you're keeping, the gases on both sides of this equation, basically, are at the same temperature and the same pressure. Okay, then, like if you carried out this, let me see, how would they? It would have to be in some volume that could expand and contract, right? So if you had if you were carrying out this reaction over some inert liquid that could come up into the container or something, what you would find is that if you combine the hydrogen and the oxygen, originally there would be 3 liters of gas in the container, right? I mean, you put in 2 liters of hydrogen and 1 liter of oxygen. You got a total of 3. You ignite it, okay, as long as your temperature is up high, so it can't form water, it's just going to be steam. You'll get 2 liters of steam. You'll see that original 3 liters go down to 2 liters. Okay. Now let me give you, let me see, another example here. if under certain conditions you can combine nitrogen and hydrogen and get ammonia. And the numbers work out 1 liter of hydrogen plus, or no, excuse me, that's backwards. 1 liter of nitrogen, 3 liters of hydrogen will produce 2 liters of ammonia gas. And just to round things out, the other gas that they discovered was actually discovered by Humphrey Davy again in sometime around 1810, I think, is chlorine. So, and they found that if you take 1 liter of hydrogen plus 1 liter of chlorine gas, you could get 2 liters of hydrogen chloride, which, if you cool this down so it turns into a liquid, is a very strong acid. I mean, it's an acid even if it's a gas, but okay, so now the remarkable thing about this, the thing that stood out to chemists that they hadn't expected, was that you would get these nice round numbers, right? I mean, in advance, there was no real reason to suspect that that gases would only combine in these small integer ratios like this. Now, do you have any guesses as to why that might be true? Daniel.
Because there aren't any partial, there isn't partial amounts of matter, there's only whole amounts of it.
Well, okay, I mean, I'm looking for some explanation in terms of the atomic theory. Okay. But what needs to be true of gases in terms of the number of atoms per unit volume, in effect, in order to make this true? I mean, in other words, well, Evan, you got an idea?
It's all, it has to be like the same.
Yeah, can you? you're right on it. I mean, the volumes are combining by these simple integer ratios. Well, if the atomic theory is right, well, we know atoms have to combine by simple integer ratios, right? I mean, that's just in the nature of things. I mean, they're atoms. So if the volumes are combining by simple integer ratios, just like we would expect the atoms to, then what has to be the relationship between atoms and volume? Troy.
The volumes are made up of atoms.
They're made up of atoms, but if, for example, let's take a liter of hydrogen and a liter of oxygen. What is, if I have a liter of each, what is the ratio of the, I mean, how many atoms of hydrogen do I have compared to how many atoms of oxygen do I have? Same. Well, that's interesting, right? I mean, what makes sense out of this whole result that we have here is the idea that equal volumes of gases have to contain equal numbers of atoms, right? Otherwise, you just don't expect these kind of integer ratios. But it's not it's not necessarily what you would expect in advance, right? I mean, some atoms are bigger and heavier than others, presumably. I mean, oxygen is many times heavier than hydrogen. Would you necessarily think in advance that equal volumes would contain exactly equal numbers of atoms? Well, that wasn't obvious to chemists at all. But once you see the volumes combining in these simple integer ratios, then that's a natural idea that, that becomes intelligible if you can equate volumes with number of atoms. Okay. Now, there's something else interesting about these numbers here, besides the fact that they're just simple whole integers. Let's look at this reaction between hydrogen and oxygen to create steam here. Now, Dalton knew that water was a combination of hydrogen and oxygen. And he assumed that, and he believed, of course, in atoms. And so Dalton figured, well, one atom of hydrogen is combining with one atom of oxygen. So his formula for water, Dalton's idea was, you've got a hydrogen combining with an oxygen. Now, does that make sense? If you've got these numbers. No, right? Because then you would expect, what numbers would you expect here? If Dalton were right, and you have just a hydrogen combining with an oxygen, what numbers should we see here? Troy?
Well, one hydrogen plus one oxygen. Well, if he was
Equals
one steam.
one steam. Right. That's exactly what you would expect. They should all be ones. Now, the fact that they're twos, there's two hydrogens to get the two steams. How do I have to modify this formula?
Two parts hydrogen.
Yeah, it looks like, let me see, is that going to work? Two, one. Now you got, so if, let me see, if we had two hydrogens, and this is just an oxygen, well, now this is a problem too, actually, right? Because on the face of it, you'd think, okay, this explains the ratio of 2 liters of hydrogen to 1 liter of oxygen. Certainly, Neve's formula does. But how many liters of steam should we get over here if we just have 2 hydrogens and an oxygen here combining. Yeah, if all you do is combine the two hydrogens with the oxygen, that should produce just 1 liter of steam over here. Because these 3 liters of gas that you've got here, I mean, there's a total, they're just completely combining. So put it this way. These 2 hydrogens, okay, they're just hooking up with that oxygen. So you had 1 liter of oxygen to begin with, okay, and that takes up, remember we've got this principle that the same number of atoms, I mean even if they're in combinations, okay, but the same number, always take up the same amount of volume, right? Well, the total, if this equation was right, the total number of steam particles produced has got to be equal to the number of oxygens that you started with, right? So this should just be a 1 here. Does everybody see that? Yeah.
Is it H combines with half one oxygen?
Half? Well, we can't have a half, right? You can't have a half an oxygen. So how do we fix this? Double the hydrogens. Well, let me see. That's a good start. Let's say that rather than these hydrogen atoms just being single, in effect, that they pair up. Let's say that hydrogen gas consists of not single hydrogen atoms roaming around, but pairs of hydrogen atoms. So let's write that as H sub 2. Okay. Does that solve our problem? Well, it does if we do this. If we assume the same thing for oxygen. Okay, that oxygen atoms don't roam around by themselves. They pair up and go around in pairs. Now let's see if it works. Go through the numbers. You have on this side of the original, you have on this side of the equation, okay, 4 hydrogens, right? You're combining 2 of these hydrogen pairs with 1 of these oxygen pairs. So you've got 4 hydrogens, 2 oxygens, and you're putting them together into 2 steam particles, which each one of those steam particles consists of 2 hydrogens and an oxygen. So you've got a total of 4 hydrogens and 2 oxygens over here, so it all adds up. It works. What? Excuse me? Oh, yeah. So, I mean, just to review for a second here. I mean, the first thing that hit chemists about what they were discovering was just these simple integer ratios, which led them to an atomic explanation, right? But then, when they go to try to explain the actual numbers, it turns out that the only way they can explain them is by, I mean, they're driven to this idea that these atoms don't just roam around in singles, that they pair up this way. Now let's see what happens. Let's look at this hydrogen and chlorine too. Now let's let's say that we've got a hydrogen combining with a chlorine atom. Now, in the water case, we needed to assume that hydrogen goes around in pairs, right? So let's say if it goes around in pairs in this case, it better go around in pairs when we combine it with chlorine too. So what does that tell us about chlorine gas now? Troy?
It goes in pairs too.
Yeah, it has to. Otherwise, there's no way you can get this to work out. Now, they could analyze ammonia and figured out that it was 1 part nitrogen to 3 parts hydrogen, by weight. Now, they know the weights of each of these atoms, and they can figure out that by analyzing the masses that it has to be this ratio of 1 to 3, 1 part nitrogen to 3 parts hydrogen. Now, again, if hydrogen is paired, what does that tell us about nitrogen? Yeah, it has to be paired. And similarly, the same thing with the laughing gas example up here. You've got a paired up nitrogen, a paired up oxygen, and the nitrous oxide consists of 2 nitrogen atoms and 1 oxygen atom. So these numbers then work out. Now this was actually a big controversy in chemistry for a while. That Dalton was always very reluctant to accept that these atoms would pair up in this way. Because at this point, chemists don't know anything about the forces that bind these atoms together. They figured that like atoms, if anything, should repel each other rather than attract and bond together. Because they knew that electrical forces were relevant to chemical reactions. And they know that, in electricity, like repels like, right? And opposites attract. So it was actually difficult for chemists to accept this idea that atoms pair up in this way, or at least now I'm not announcing this as a general principle, okay, that all atoms pair up like this, but it turns out that for the common gases that they knew about, it's true that in the case of nitrogen, oxygen, hydrogen, and chlorine, which were the 3 elemental gases. I mean, 4 elemental gases that they knew about at this time. In all those cases, the atoms combine in this way. And they were just driven to this idea. They didn't expect it at all. They were just driven to this idea by the way these numbers came out and the way the volumes combined. Okay. Now, does everybody get that? Now, these are, these chemical equations that I'm writing on the board. I mean, the main way to check any such reaction, one thing you always have to check on is that you have the same number of atoms on one side than you do on the other, right? Because atoms can't appear or disappear. So just that basic conservation of matter principle in combination with this principle that equal volumes of gases contain equal numbers of molecules led them to this result that these gases pair up. Now, I just introduced a new word, molecules, and I should explain that. But I'm done for this morning, I guess. We'll continue this afternoon.